You type a quick message to a friend across the world and tap send. That signal travels through the air for just a few feet before hitting a local router. From there, it immediately plunges into a buried physical grid. Look at these workers hauling massive cables out of the surf. These armored pipes lie directly on the ocean floor, physically tethering continents together. But how exactly does your text message travel through thousands of miles of underwater pipe in a fraction of a second, entirely without electricity? To understand how global communication actually works, we have to look past the wireless illusion and zoom all the way down to the microscopic, highly engineered physical machinery that silently moves all of the world's data. If you slice open a heavy submarine pipe, peel back the polyethylene jackets, the steel strength wires, and the plastic tubes, you won't find a massive copper wire inside. Instead, you find a bundle of individual strands. You might hear telecommunications engineers call a setup like this a 144-core cable. That doesn't mean a single cable has 144 cores inside it. It means the cable contains 144 separate, distinct optical fibers. Cull just one of those individual fibers out of the bundle. It's incredibly fragile, and the entire structure is roughly the thickness of a single human hair. The entire weight of global finance, streaming video, and daily communication relies entirely on the structural integrity of these microscopic threads of glass. This diagram shows a fiber's cross-section, divided into two layers, an inner core where light travels, and an outer cladding. To keep light trapped, the core's glass is manufactured to be slightly denser than the surrounding cladding. Look at this technical diagram of light at a glass boundary. When light hits the boundary between the denser core and lighter cladding at a shallow angle, it triggers total internal reflection. Instead of leaking out, the light rays bounce perfectly inward. By continuously reflecting back and forth against that boundary, the light is effectively trapped. It creates an inescapable highway that propels pulses of light forward at extreme speeds. By trapping light using minute differences in glass density, engineers solved the physics problem that makes modern digital networks possible. Inside a wide core, light takes many bouncing paths. Wider angles travel further, arriving out of sync and scrambling data, causing modal dispersion. To fix this, graded index cores decrease glass density toward the edge. Outer beams travel faster through less dense glass, arriving simultaneously. But even graded index technology degrades over thousands of miles. It isn't precise enough to carry your text message across the Atlantic. For transoceanic distances, networks use single-mode fiber. The core is manufactured so incredibly narrow, just 8 or 9 micrometers across, that the light physically has no room to bounce. It's forced into one single, straight propagation path. By restricting the light to a single mode, the signal avoids dispersion entirely, allowing the message to cross the ocean completely intact. Creating a glass core that narrow requires massive industrial equipment known as a fiber drawing tower. Inside the tower, a large rod of highly pure glass, called a preform, is heated to 2200 degrees Celsius. Protected by an inert argon atmosphere to prevent oxidation, the glass softens and stretches downward into a microscopic thread. The machine pulls the molten glass into a precise 125 micrometer strand at speeds exceeding 10 meters per second. Because bare glass is fragile, it immediately passes through intense UV curing lamps. This instantly hardens a protective polymer coating around the fiber before it can be spooled. The reliability of the global internet begins inside this tower, where 2200-degree heat and sub-micron precision transform raw silica into the glass threads that power the world. After crossing the ocean floor, those microscopic light pulses complete their journey and slam into an optical receiver inside a destination data center, looking a lot like this server room. That receiver instantaneously converts the photons back into electrical pulses, the binary logic that computers can actually read. The converted data then travels the last local mile, routing to a cell tower and finally arriving on your friend's phone screen as the word hello. Every message we send relies on this intricate physical network, a global machine of microscopic glass and light that binds humanity together.